Everyone is talking about agentic AI. I
Yeah.
mean, it is absolutely the buzzword of the year.
Oh, without a doubt.
We've officially moved on from chat, which was cool, to agents, which sounds, well, a lot more profitable.
It does. The promise is incredibly seductive. You just tell the AI, hey, book my travel, manage my global supply chain, and it just does it.
It just goes out into the world, uses tools, swipes credit cards, and executes. It's the ultimate delegation fantasy.
It is. But we've got a stack of sources today that suggests we might be popping the champagne just a little too early.
Oh, here we go. A buzzkill right off the bat. But I like it.
It's a necessary one. What we're looking at today is a presentation called Beyond the Hype, and it's pulling from some really dense research. We're talking Stanford, OpenAI, Apple ML research.
Okay.
And the central argument is fascinating because it doesn't say the code is bad. It says the physics are wrong.
Physics? Wait, we're talking about software. How do physics even come into play here?
Computational physics. The argument is that there's this hard ceiling on what these models can actually do, and it's not imposed by how smart they are or how much data they have. It's imposed by the mathematical complexity of reality itself.
Okay, let's unpack this. I'm looking at the deck right now, and the first visual, it sets a very specific tone.
It really does.
It's got this precise, technical blueprint aesthetic.
Yeah.
Very Silicon Valley. But then someone has scrawled this massive, hand-drawn orange not equal sign right over the middle.
Crossing out the connection between agentic AI and omnipotent, it's a reality check in visual form.
But the fine print here, it lists some heavy hitters. PVS-NP problem, quantum decoherence, Gödel's incompleteness theorems. It feels like we stumbled into a theoretical physics class, not a tech meeting.
And that's the point. It's not about scaring people. It's about grounding expectations. The whole mission of this deep dive isn't to say AI is useless. It's to debunk the idea that these agents are magic wands.
Right, that they can just solve any problem you throw at them.
Exactly. We need to bridge that gap between the marketing promise, it does everything, and the hard constraints of math.
Okay, so if the mission is to stop treating it like magic, what do we treat it like?
We treat it like a tool that needs a very specific kind of handler. Later in the deck, they introduce this idea of the data apprentice path.
The new way for humans to kind of engineer around these limits.
Precisely. But before we get to the solution, we have to really understand the trap.
Fair enough. Let's look at the trap on the next slide, the agentic promise. This is a diagram we've all been sold, right? It's a nice, clean flow chart.
It is. On the left, you've got retrieval. That's your standard chatbot.
Yep.
Then an arrow to tool use, the AI clicking buttons, and finally on the right, agentic AI. Big gears turning. It looks like a natural evolution.
Like Pokemon evolving.
Exactly. And the context note here mentions the market is betting everything on this. We're talking agents managing industrial equipment, executing financial transactions with no human oversight.
But you're pointing me to the bottom right corner, that little sticky note.
I am. The one under the conflict.
It asks, can the math actually support the promise? That's the multi-billion-dollar question, isn't it?
It really is. And this brings us to probably the most alarming graph in the whole deck. Let's go to the next one, the hard ceiling.
Okay, this graph is stark. It charts problem difficulty versus how much brain power you need to solve it. 2 lines.
I want you to trace them with your finger. Where do they go?
Okay, so there's a blue line, LLM capacity. It curves up gently, like a nice steady hill. But then there's this orange line, real-world complexity.
And that one?
That thing doesn't curve. It just shoots straight like a rocket. And there's this huge red shaded area between them.
Labeled the hallucination gap.
The hallucination gap.
That gap is where the money is being lost. The slide cites the Sika et al. Theorem. It sounds technical, but it's simple enough to get your head around, and it changes everything.
Okay, explain it.
Transformer models, the tech behind ChatGPT, Claude, all of them, they process information in what we call polynomial time. Roughly speaking, that's O of n squared.
Okay, pause. Polynomial time. What does that actually mean for me?
Think of it like a dinner party. You invite one more guest, you maybe add one more chair, cook a little more food. The effort grows, but it's manageable. That's polynomial.
Got it. Manageable growth.
But the real world, logistics, encryption, scheduling, a lot of those are exponential problems. That's the orange rocket line.
Okay.
In an exponential problem, adding one more guest isn't just one more chair. It's like Now you have to seat everyone in a specific order based on who they like, and with every new guest, the number of possible seating arrangements just explodes.
So it goes from grab a chair to millions of combinations almost instantly.
Instantly. And you cannot solve an exponential problem with a polynomial engine. It's a fundamental mismatch. If a task needs more computational steps than the model has tokens, it must hallucinate.
Wait, must? You're saying it's guaranteed?
Mathematically, yes. It's not that the AI is, like, lying to you. It's that it literally runs out of computational runway. It hits the wall of its own complexity limit, and to finish the sentence, it has to guess.
See, that is a wild way to think about it. I think most of us assume when an AI gets it wrong, it's just being dumb, or it was trained on bad data.
Right, a personality flaw.
But you're saying it's not a flaw, it's a physics limit.
Precisely. And the deck gives a brutal example of this on the next slide, the one with the map.
Yeah, where verification fails. This looks like a nightmare airline route map. It's the traveling salesperson problem.
I think we all remember this one from school. It sounds easy, right? Find the shortest route between a bunch of cities. But finding the perfect absolute shortest route is mathematically factorial.
Which means as you add cities, the number of possible routes just explodes into the trillions.
And the map here is covered in these orange markings: failed route, missed cities, and these big orange question marks.
Those question marks are the hallucinations.
That's the model just guessing, because the complexity exceeded its depth. The slide lists other impossible tasks too. Token composition, precise matrix multiplication.
Composition.
Yeah.
That's like asking you to spell a word
Yeah.
backwards or do a cipher.
Right. If I ask an LLM to list all possible strings of length 10 using these letters, it will fail. Not because it doesn't know the letters, because it can't hold that exponential state in its working memory. It'll just start guessing strings that look plausible.
But hold on, I have to play devil's advocate here. Silicon Valley has an answer for this. They say, okay, the bot is dumb, so we just build a manager bot.
Yes.
You have a worker agent and then another agent to check its work. Problem solved.
The manager-agent fallacy. That is literally the title of the next diagram.
It is. It shows a worker agent solving a maze and a manager agent holding a clipboard. But there's a big red warning sign, an equation.
O of verification is greater than O of solution.
What does that mean?
This is crucial, and it's where most companies get burned. They assume checking the work is easier than doing the work.
Well, usually it is. If I ask you to solve a math problem, it might take 10 minutes. I can check the answer key in 2 seconds.
For simple math, sure. But for these NP-hard problems like complex routing or encryption checking, the answer can take just as much, or sometimes more, compute than solving it.
Why? How is that possible?
Imagine cracking a password. The worker agent guesses a password. To verify if it's the best or correct answer, the manager agent has to basically recalculate the entire problem to be sure it doesn't have a cheat sheet.
So if Agent A is dumb, Agent B is just as dumb.
It is the blind leading the blind. If Agent A hits a compute limit and hallucinates, Agent B, which has the exact same limit, cannot possibly verify the answer. The slide puts it perfectly. We cannot replace human in the loop with agent in the loop for NP-hard tasks.
Wow. Okay, that's depressing. We're stuck with a system that can't do the hard math and can't even check if it did the math wrong. So why does it act so confident?
That is the question.
Why does it answer with such swagger? Here is your optimized route when the route is total garbage.
That brings us to the psychology of the model. The next slide is perfect. It's called the test-taker syndrome.
I'm looking at these bar charts, a comparison of pre-training versus post-training.
Now follow the orange arrow on that right-hand chart.
Whoa, the bars shoot way up. It's labeled overconfidence.
Here's what's happening. The pre-trained models, before we fine-tune them to chat with us, are actually pretty well calibrated. If they don't know something, the math inside them basically says, I don't know.
But then we train them.
But then we do reinforcement learning. We train them to be helpful. We give them points for answering questions.
So we're incentivizing them to answer, even if they have no idea what they're talking about.
We're rewarding guessing. The benchmarks we use to grade these models don't usually give points for staying silent, so the model learns to bluff.
Oh, man. That sounds exactly like me in my high school calculus final. I didn't know the answer, but I wrote down a lot of numbers hoping for partial credit.
That is exactly what the AI is doing. It's trading honesty for points. It has learned that humans prefer a confident hallucination over a humble, I don't know.
That explains so much. But what about the new stuff? The reasoning models? O1, DeepSeek, They're supposed to think before they speak.
Right, let's look at that slide, the reasoning illusion.
This visual is great. The top shows a standard LLM, just a straight blue line to the response. But the bottom shows a reasoning model with this long chain of blue blocks called think tokens before the response.
It looks like it's showing its work.
It does. But look at the end of the chain. It's still crashing into a brick wall labeled exponential complexity.
That's Sika's analysis again. Reasoning models, they add more linear steps, they extend the horizon, they can think longer. But think back to our analogy.
The dinner party.
No, the other one. Adding more thinking time is like walking further down a road. It helps you get distance. But if the problem is jump over the Atlantic Ocean,
Walking further down the pier isn't going to help.
it doesn't help. Reasoning models still fail at exponential problems. They just fail a bit slower. It looks like thought, it feels like reasoning, but mathematically, it's just a longer chain of next token predictions.
Okay, that is a heavy reality check. We've smashed the hype. We've established the hard ceiling. I feel sufficiently humbled. But this isn't a give-up deep dive, right? The deck pivots here.
It does. The next section, strategic synthesis, is where the vibe shifts from problems to solutions. This is where we stop complaining about what the AI isn't and start talking about what we are.
There's a great quote here. We are trusting probabilistic poets to do deterministic math. I love that line.
It's perfect. And the solution isn't better prompting, it's a new role. The slide calls it the system architect or data apprentice.
The diagram shows a human sitting in the middle. On one side, the probabilistic interface, the LLM. On the other, deterministic tools like Python and SQL.
And the headline says, you are the logic.
So we aren't just asking the AI to do the work. We are building the rails for it to run on. Let's get into the skills because this is the actionable part.
Okay, let's look at the next slide, the skeptical operator. Look at the code snippet on the left.
I'm looking at it. It says, instruction. Answer this question only if your internal confidence is 90%. If below 90%, output token IDK.
That's a calibration failure output. We have to force the model to admit when it's ignorant. But the real insight here is on the right. That chart about singletons?
Singletons? I don't know that term.
A singleton is a fact that appears only once in the AI's entire training data. Imagine a specific obscure date from a memoir that was only scanned once.
Okay, so a very rare fact.
And the chart shows that for frequent facts, stuff that appears everywhere, like the sky is blue, the risk is low. But for singleton facts, the hallucination risk bar is skyscraper high.
That is terrifying for business. Because usually the specific rare facts are the ones we actually need.
They're the ones that matter. So the rule is, if you're asking about a singleton, treat the AI's answer as radioactive. Assume it's wrong until you can verify it yourself.
Radioactive. I like that. Okay, that's short term. What about medium term? The next slide talks about systems architecture. It contrasts the old way versus composite systems.
This is the biggest level up for anyone working with AI right now. The old way is you prompt, solve this route, the LLM guesses, and you get a hallucination.
And the composite system.
You prompt the LLM to write Python code. That Python script then solves the route, and you get a deterministic solution.
Ah, I see. So you don't ask the LLM to be the calculator, you ask it to call the calculator.
You got it. The LLM is the interface, the code is the engine, the skill focus is clear. Strengthen your Python and SQL foundations. You have to know enough code to verify that the logic rails the AI built are actually sound.
So you can't just be a prompt engineer anymore. You have to be a flow engineer.
Flow engineering is the new prompt engineering.
Right.
Absolutely.
And you have to grade it differently. This evaluation engineering slide is brutal. The scoring matrix.
Look at row 3. That's the one that matters.
Row 3, wrong guess, hallucination. The score is -5, a severe penalty.
See, most benchmarks just give 0 points for a wrong answer. But think about your job. If you don't answer an email, that's a 0. Annoying, but fine.
But if you answer the email with the wrong financial figures and the company loses $1 million,
That's a firing. That's a -5. We have to design tests that reward the model for saying I don't know and massively penalize it for bluffing. We have to deprogram that test taker syndrome.
that changes the whole incentive structure. It's basically parenting the AI. I won't be mad if you don't know, but I will be furious if you lie.
100%.
Okay, let's look at the long game. The final section, managing the flock. This visual is chaotic. It's a network of nodes, little cubes representing agents.
And notice the red arrow spreading out from the center. Cascading hallucinations.
It mentions society of mind risk. That sounds like something from a sci-fi horror movie.
It's not far off. Imagine you have a fleet of agents. Agent 1 drafts the strategy. Agent 2 researches the market based on that strategy. Agent 3 writes the code.
Okay.
If Agent 1 hallucinates one small fact, say, it invents a competitor that doesn't exist. Agent 2 will then research that fake competitor. Agent 3 will write code to fight that fake competitor.
So a small lie at the start becomes a massive system failure by the end.
Correct. By the time it gets to the fifth agent, the hallucination has become truth. The role of the human is to audit the logic between the nodes. You have to catch the whisper before it becomes a scream.
We need a cheat sheet for this.
Yeah.
And thankfully, the deck provides one. The reality check decision matrix. This is something everyone listening should probably pin to their wall.
It's a triage system. Let's walk through it.
Okay. First diamond. Is it computational, math logic, that kind of thing?
If yes, use a composite system. Make it write Python. Don't let the LLM do it alone.
Got it. Second diamond. Is it factual? History, documentation lookup.
If yes, use RAs plus a calibration check. Verify the source. Trust the document, not the memory.
And the third diamond. Is it creative? Drafting an email, brainstorming?
Then yes, a raw LLM is fine. A hallucination here is just creativity. It's okay if the poem's weird.
But there is a massive orange box at the bottom. The golden rule.
Read it out. It's important.
If task complexity is greater than model compute, the answer is a hallucination.
Memorize that. If you ask a polynomial model to solve an exponential problem, you are not getting an answer. You are getting a dream.
Which leads us right to the final slide, the future architect. It shows this human figure standing next to a massive, complex blue structure of blocks and girders.
And the text says, your career will not be defined by how well you prompt the AI. It will be defined by how well you build the systems that mitigate the AI's limitations.
Physics and statistics are the constraints. You are the engineer. That is empowering. It feels like we're graduating from just talking to the bot to actually building the factory that contains it.
That is the shift.
Yeah.
We're moving from prompt engineering